I think we have the next speaker with us.
The next speaker is in the room, Paula?
No, it's online.
Oh, okay. Thank you very much. So, yeah, our next speaker is going to cover lessons learned from gas reactor PRA efforts. If you could please introduce yourself, and you're welcome to start.
Good afternoon. My name is Serbanescu. I'm currently an employee of Nuclear Electrica in Romania, which is an operating nuclear company. We are operating CANDU 6 reactors, 2 CANDU 6 reactors, 2 are under completion of construction. And we are also in a project of SMR, light water SMR. So I'm involved in the safety and risk aspects of all those projects. But today I prepared for a presentation the experience I got, and it is included in a project on another professional tasks I'm performing in the divisional logic of our academy related to the way we are learning lessons from innovative designs in various areas, technical areas, including in nuclear. So I performed between 2002 and 2006. I was a technical coordinator and a senior expert in a PRA study level 1, 2, 3, internal and external events in PBMR Limited in Pretoria, Centurion, Pretoria. So I'm going to share some of the findings from that time. I would like to draw your attention on the fact that many of the things I'm going to say, they now may look common, but these are lessons derived by 2002, 2003. So it proves that they are more or less confirmed by further results of the community. So the background of this presentation, the main issues and some conclusions. So the background is this experience from PBMR, but not only, so because all my life I performed safety and risk analysis, real ones. I'm at the grass level operation work. So as far as PRA is concerned, PRA in PBMR was a real challenge because the target was threefold. From one side, we had to derive a list of postulated initiate events, which was quite in clouds by that time. Another task was to support the design, actually to do it, not only to talk about it. And the third was to develop a PRA at least of class 2, if not of class 1, in accordance with ASME classification, so that it can be used for licensing. So that means that it had to be in accordance with the standards, and we followed the US NRC standards, NUREC 2300, NUREC 1150, and so on. So on all aspects, including on the way the team was composed, the organization, and so we're actually working as a project with limited budget, limited time, and tasks, and people in various levels of knowledge requiring training. So this was a real life task. Now, related to what we can derive from that, I realized now later on, recently, when I looked in various IAEA documents, that more or less the topics I'm going to talk about, they are identified as issues which may require more attention, if not change, when we talk about gas reactors, in order to be in compliance with the existing IAEA guidances and requirements. These are the lessons learned. I will refer to 9 of them. There's a lot of them, but I thought these 9 are representative. The first one is related to the way we had to define what is the defense in depth actually for this plant. And here we had to give answers to 2 types of questions. The first was how independent are they? And the second was what kind of method do we use in order to show the fact that we cover and the line of defense from one level to another one, which, as you can see here in the lower part, may lead to a situation that we have uncovered a feature of a line of protection at one level, let's say level 3 or level 2, then it has to be covered at the next level. So in order to model that, we can and we did use a combined approach. We didn't invent anything because the combined approach of success scenarios, how to do it to succeed, and failure scenarios, which are the probabilities that the systems, the barriers assumed to assure the protection for a certain line of defense will not fail. So there's a combination of success and failure approaches. This was not new, and it exists, as you can see here. It existed, and I was inspired, I recognize that, from the can-do philosophy, which in the 70s, they were using this combination of success modeling, success path modeling, the so-called safety design matrices, and the failure tree modeling, the reliability analysis for important safety systems. So from these two combinations, they were actually screening as complete as possible at this level of study, of this evaluation, the capability of the plant to cope with various initiating events. And then we had to derive the list of initiating events. And for that, we built a model. And the model was built in Respectrum in a network format for all the team. We had 3 persons in the team. Each has their tasks. We interacted with engineering and CFD calculation, deterministic calculation groups, and we evaluated a huge amount of scenarios and for these success paths and a huge amount of possible failure modes using FMECA and HAZOP for various systems and components. And this was the first phase of the PRA. Now, the second lesson is related to the fact that we realized from the very beginning that the important thing is not. Of course, it is important to have a certain number, and the way the barrier, the way the levels of defense were defined in the IAEA documents, and this is proven and so on. But it might be, we thought that from the very beginning that we have some special cases, and that's the case in this case. For instance, one of the first barriers, which is the fuel, actually has more than one line of defense, so it has more layers in order to protect. So it is much more powerful than a normal thing. And by the way, this is a thought from a project in which I am now currently related to accident-tolerant fuel. So yes, the people who actually derived the BISO and TRISO thing, so they, in my view, they went on the very solid ground of improving the safety in the sense that the first barrier is a very important one, and this is the fuel. So we modeled that, and we had, but in order to model the failure modes and the way we can consider that we have a core damage, and what is that, a core damage in such a reactor, we had to work closely to the engineering and safety calculation teams. The third lesson, which is the second part related to those layers, was related to the containment. So we actually, what is that containment in this case? As various comments were even in this meeting before, we are dealing with a thing, with an industrial source of risk, which has 500, 600 degrees Celsius, is highly penetrable substance, and 80, 90 bars. How can we contain that? And that's why, so the concept of containment is on the functional level, as it was mentioned several times. it was not so obvious by the time we were working on that. So in order to evaluate how the containment will behave, you will see here a drawing, a schematic drawing, but actually it was much very well detailed. Trying to figure out is showing here the paths that could follow, that could be followed by a flow in case that we have an immediate release and a delayed release. And here you have a huge amount of, they look like Excel files, but they are actually versions of success trees in the respectrum model, in which we assumed the credibility of one path or another, a certain split fraction for a certain path, and we ran a lot of cases. The keyword here is sensitivity analysis, parametric sensitivity analysis. We performed a lot of them, maybe thousands, maybe more runs in order to evaluate which are the critical ones. Then and the next lesson was why do we do that? So because in the third task we had, they almost didn't care about the level of knowledge of the team, the novelty of the topic, and so on. We got to deliver a PRA so that to send to the NNR, to the regulator, and to be approved. And the requirement was that as of an old plant, well known, which complies with the standards, at least in PRA, because this was our case, the PRA, we were looking at PRA. So for this, from this perspective, it was very important the way those licensing requirements were derived. We were part of the interaction of PBMR team with the regulator in defining the rules for that, so the various categories. I'm glad that I recognize that in other projects which were presented before. But again, this is 2002 when we were talking about that. And they were also formulated in figures. So we did have some safety objectives, and we had to prove that PRA. Why we followed the PRA level 1 to 3 internal and external events? Because the trend, even by that time, was obvious that for the next generation, generation 4, we have to look, core damage frequency becomes less relevant, LERF becomes less relevant, the important indicator will be the total risk. So we needed to perform a PRA level 3 and to deliver a product to the level 3. On the other side, we had to have an integrated model in Respectrum. This is a huge model. It's a pity that the knowledge was lost. There are only some partial communications which are available. I listed them, but it was a huge work because we had to perform a lot of sensitivity analysis in order to show that we are complying with the safety objective. The next lesson, which started by that time, but I am working on some of the follow-ups now when we deal with SMRs of other type. Emergency planning. Yes, basically everybody claims that there is no need and so on. However, the requirement to have an emergency planning exists. So you have to prove that you don't need it, or if you need it, of what type. So for that, we built so-called decision trees, which are integrated with the PRA level 3 model. So imagine a decision tree, which is actually a subjective tree, integrated to the results from PRA in the same Respectrum model. And in order to derive the emergency action levels, based on which the levels for various emergency planning actions are derived. Then in the same model, we model the entities actions and various operator and entities actions in order to cope with various situations. Alarm, emergency on site, emergency on surrounding area, and so on. So also to mention here, an important thing is that these evaluations actually trigger the question which was also mentioned previously yesterday, related to the fact how sound, how applicable are some of the Bible type rules in safety, like for instance the 3C. So how do we interpret the contain rule for the containment? Because and I will not mention too much explanation about that. I showed some things we did, and I also mentioned the fact that the delayed release is by far much more dangerous. And that's why the important thing is, in this case, is to show that you meet the safety objectives. Now, if we apply the probabilistic evaluation, then we'll get, for each of the zones, we'll get a range, a lower bound and an upper bound. And that range depends on the way the inputs was calculated. Again, this is a first of a kind thing. We obtain things which have extremely high level of uncertainty. So the key word, in my view, after performing all of these activities for almost 5 years, is perform sensitivity analysis, parametric sensitivity analysis, as much as possible. And if you do that, now mention the fact that there are differences between the way we calculate those radii in deterministic manner and in probabilistic manner. When we calculate in probabilistic manner, we actually end up not with just multiplication of probabilities, we end up with the convolution integrals, which is something different. And when we talk about more than one modules, then we have to be careful about the way we define the radii. It might be, in order to be sure that we don't evacuate the people, because and we are still in the range of uncertainty of the exclusion area, and because of the error range, we take a wrong decision. Now, the next lesson is related to what kind of method to use, probabilistic or deterministic. This is something we derived for our purposes. This is an illustration of a lot of calculations and evaluations, which shows that it depends what we want. It depends what we have. So if we count on credibility in the assumed conservatism and or in the credibility of the uncertainty results, then we may have a quadrant of various possible combinations of uses of deterministic versus probabilistic things. And depending, as you can see here in the lower part, depending on the goal of that PRA, whether it is done for postulate initiative and list derivation. By the way, we had tens of thousands of PIAs, and then we grouped them. It's not only one, not only 5. We just thought this might be. No. So we took systematically all the possible combinations using the method I presented in the lesson 1 and derived this pi. Then we use that for design. I personally, together with the project manager, Henriette van Graan, we were part of the change control board. So every time they were changing something in the design, we had to run our model and to say whether that will lead to an increase in risk or decrease in risk. This is the second application, and that's why the method depends on what we want. Why do we run it? And the last is licensing. In licensing, the regulators, at least in our case, almost didn't care about the fact that it's a first of a kind. You don't have failure. I see a lot of PRA communications and so on about new type of regulators. I have simple questions like, how did you derive the failure rates for certain type of components? For instance, in order to derive the failure rates for the pipes, we had a special contract with a specialized team from General Atomics in the United States, so that to make a translation from existing databases to the failure rates in the gas pipes, so in a helium pipe. So it's not so easy. So yes, you can write there any number, and that shows the fact how far away from the reality you are with your PRA model. Now, when we combine various type of approaches, for instance, here we represented several groups of possible approaches, which are combined, probabilistic and deterministic, and the way the applicability of their applicability depends on where you are when you look at the ratio between the risk you would like to achieve, you may have for that initiating event, for that group of initiating events, and how the safety function is fulfilled. In other words, what is the safety margin you have? If you have a high safety margin and a medium safety margin, then you'll use, I'll mention further which one. You'll use one method. If not, if you have a low safety margin, you'll use another one. Our conclusion was that if you have a low safety margin, go back to the deterministic analysis and then come back and do another iteration. If you have at least a medium and high margin, then you may perform PRA because it will be not such a science fiction type of calculating probabilities in squares and lines. Now, this is the way the PRA level 3 results look like. And it's a lot of work. So what is important from here? It is done from various distances from the site. By the way, we also included calculations up to 400 meters. And various release categories, immediate release categories, delayed release categories of the fuel in operation during shutdown. By the way, we had to model also worker risk. And in order to do that, you have to have a certain maintenance policy. It's not a simple thing. This is a high dangerous area where people has to get in order to perform maintenance. So how do you model that? We did have a model, not invented as much as the safety engineers groups gave us information. It was quite detailed and reasonable. Now, the seventh lesson was related to the use of risk in the design phase. I mentioned something about that. It's in steps, iterations, and a continuous work. This is not only one model of PRA. 1, 2. This is not a model of PRA level 1. You have to take it to level 3 and to have integrated models of internal and external events. By the way, integrating internal model of PRA with seismic PRA, for instance, or tornado PRA, for instance, is not a simple thing. And I'll be glad to have discussions with experts in PRA talking about that, because it's a huge, new, very, in many cases, unknown methodology to do that. Not talking about the fact when you talk about multi-modules. So the PRA first starts from the type of sketch I mentioned in order to derive the list of initiated events. Then we developed a model for the design optimization, and we actually used it. We have even communicated papers with real cases when we were asked about the impact, and we gave an answer. And using this model, and then we had to develop a model for the licensing, and we did that. And it was reviewed independently by a United States consultant coming from General Atomics branch. And it seemed that we are on the right track. So we are not quite close to level 1 because of the fact that we didn't have databases and many other things. And that's why I'm very reluctant when I hear about the fact that, yes, we perform PRA and so on, and it's the first of a kind. And they don't mention that. I'm reluctant in the fact that even the magnitude of the problem is understood. And we did that for this level of knowledge by the time, with the limitations that resulted from here, and the lessons learned for the future. Now, another lesson, which is a little bit, will look a little bit strange here, because we are talking about operating regimes and plant applications, and you see here some figures which show the thermodynamic cycle and so on. I'll mention again. The fathers, the fathers of PRA mention something, there are two lines in NUREC 2300. When you start something from scratch, you just have a diagram, a thermodynamic diagram, a reactor physics diagram of that. So the first indicator you have about possible areas of risk increase is more or less in compliance with the axis of loss of exergy, loss of entropy within that cycle. And I added here the idea also loss of control, because this is a controlled installation, controlled thing. The last lesson is related to the fact that we are talking here, and maybe I missed, we are talking only about the plant and only about the nuclear technology. Nuclear power plant is a technology. That's why it complies with an S-curve, because it is a technology. So it has the beginnings, then it has the improvements, and then it has the asymptotic stage, and it has the end. So, and in the meantime, from time to time, it has some bumps, which are the accidents, which show how different is what we think we got by comparison what it is. And we go back to the drawing table, as it happened last time in Fukushima case. That's one thing. Another thing is that this is a technology. This is not only the technology of reactor core or the thermodynamic cycle. It's an envelope of technology. There's a technology of INC, the technology of manufacturing, the technology of managing, the technology of leadership, the technology of people. A lot of technologies. There's a lot of science here within a nuclear power plant. And that's why not talking about the fact that nuclear power plant is not something isolated. It is something, it has a front-end part of the cycle and a back-end part of the cycle. So we have to have all of that in mind when we evaluate a plant. And here is an illustration, more detailed illustration. You may find in the things I referenced details, and actually for all of those I have detailed presentations in the links included in the beginning, which show that we moved in our, yes, we did have accidents. We did that because we usually make confusion between FOAC and NOAC. Usually we are paranoidally optimistic, and usually we discard the fact that we may have accidents. And we did. So far, there were 5 major accidents, which actually brought us down to the ground and forced us to rethink many things, including the last one. Every time the paradigm, safety paradigm changed. Now we have one, and we will change it also. I could have predictions, but I will not stop it. And the last thing I wanted to show is that this is not in an isolated globe, nuclear. It's in the context of the industrial revolution. We are going to face. So we are building now a plant for 50 years, 60 years, 2090, 2100. This is going to be Industry 4.0. This is not only robots. This is artificial intelligence. There will be many types of management. Who knows which types, and or leadership. But mainly there will be other people. So now when we derive and I will give this example because usually it's almost absolutely discarded. When we design a control room, we actually forget that control will be used by somebody 20 years from now, 30 years from now. How the world is going to look like, how the people are going to look like, which are going to be their abilities, which are going to be their limits. And I think this is also to be considered, especially on this generation 4 type of reactor. So we actually discard the fact, for instance, that maybe in 20 years the manufacturing will count on nanotechnology and printing procedures. So, but we still consider and take into account the same technology as before. No, not talking about the people, as I mentioned. So the conclusions are that, yes, there are lessons. Many of them are applicable to many other types, not only to gas reactors. For the gas reactors, we could feel comfortable that our judgment was correct in 2002, and many of those things are now confirmed and studied in detail. Thank you very much.
Thank you very much. Some very insightful observations and some key considerations for us going forward. I don't see any questions in the chat. Does anybody in the room have a question or a follow-up observation for Dan?
Yes, we do. We have. Please, Karen.
Karel Knopper, Tractable. Thank you for a very, very interesting presentation. I was wondering, did you, from this exercise back in time, did you have any specific lessons to learn how to look at the passive safety systems in the PRA and also in relation this to external hazards?
Yes, I think there are two questions. For the passive features, we had a contract with Technology Insights. They applied Markov chain technology in order to model the passive failures. And one of the applications of this methodology was related to the failures in the pipes. And we got the figures we got were derived based on this methodology. The second part is for the external events. We did have a challenge, a big one. By the time we developed the model, there was not a custom as it is now to have integrated models of the external PRA into seismic PRA, for instance, into the internal model PRA, because it's a question of technique, the way you are including various logic trees and switches and so on. And we did, that's what we did that. And in order to do that, we initially performed some tests, how to do it. Then we wrote some reference papers and submitted to Bob Budnitz in the United States and reviewed it. And then we implemented at full scale in the model, and it worked.
Any more?
Thank you very much. Any other questions in the room?
I don't see any hands, Tim.
Okay, thank you very much, Dan. I'd like to move on to our last presentation for today before we'll take a short